All right, let's dive into something fascinating, the unseen engine of science. We're going to pull back the curtain on how science really works. Specifically, how we take all the messy, chaotic facts of the real world and somehow turn them into these clean, elegant theories. It's a bit of a magic trick, and we're about to find out how it's done. So here's the big puzzle we need to solve. I mean, think about it. The real world, it's messy, it's chaotic, totally unpredictable sometimes. But the scientific theories we use to explain it, things like Newton's laws or the theory of evolution, they're just so clean. They're perfect, structured, elegant. So the question is, how on earth do you get from that messy reality to this perfect theory? What's the bridge that connects those two completely different worlds?
And you can really see that divide right here. On one side, you've got your empirical facts. These are noisy, they're full of exceptions, just endlessly complicated, like trying to predict the exact path of a single leaf falling in the wind. Good luck with that. But then, on the other side, you've got the theoretical models. They're simple, they're rational, totally idealized, like that beautiful, clean equation for gravity. It's like they're speaking two completely different languages, right?
So, what is that bridge? What's the secret sauce? Well, it's a process called scientific fitting. Seriously, this is the unsung hero of how science gets done. It's the engine room, the hidden machinery that makes everything else possible. Okay, so what is scientific fitting? Well, simply put, it's the crucial process of getting those raw, messy facts to line up with our clean, rational models. It's not a passive thing at all. You're not just observing the world. You're actively trying to build a coherent picture by, getting those two different languages to talk to each other. And this is really the key takeaway here. It's an active process. It's almost like you're immersing the facts, plunging them into the world of the theory. This means science isn't just about passively discovering stuff that's already out there. No, it's about actively constructing a framework and then meticulously, carefully fitting reality into that framework. Okay, so how does this fitting actually work? What's the mechanism? Well, the main tool scientists use is a concept you've definitely heard of, but they use it in a really specific and powerful way. That tool is abstraction.
And this process of abstraction isn't just one thing. It's more like a three-step recipe. First, you have to translate the facts. Then, you reduce their meaning. And finally, you idealize them. Translation, reduction, idealization. That's the core mechanism right there.
So, let's break that down. Step 1. Translation. The best way to think about this is that abstraction acts like a dictionary. It takes a raw observation from the real world, say a red apple falling kind of fast, and it translates that into the clean, formal language of a theory. So red apple and kind of fast become precise concepts like mass, velocity, and acceleration. All right, step 2, semantic reduction. Now, that sounds super technical, I know, but the idea is actually pretty simple. Once that fact is translated, its truth is now judged based on how well it fits inside the theory. All its other real-world baggage, the fact the apple was a Granny Smith or that a bird flew by, that all gets set aside. Its meaning is reduced to only what's relevant for the theory itself. And that brings us to the final step, idealization. Look, pretty much every scientific theory you can think of is built on these idealized concepts. You've heard them before. A frictionless surface, a perfect vacuum, a point mass. None of these things actually exist in the real world, right? They are, by definition, different from the raw facts. And that's exactly why scientists need these rules of reduction, to connect their perfect, idealized concepts back to our messy, imperfect reality. Okay, that's all great when things go smoothly, but what happens when they don't? What happens when a fact just refuses to fit into the model? When the data you collect seems to completely contradict the theory you're working with? Now, this is where things get really, really interesting. Take a look at this quote. It's kind of shocking, right? It says that achieving objectivity can involve the elimination of data that contradicts the model. I mean, what? That sounds completely backward. It almost sounds like to build a perfect theory, you have to just ignore the bits of reality that don't play along. But hold on, there's a crucial piece of context here. This elimination isn't about cheating or hiding the truth, not at all. It's actually part of a super rigorous cycle of testing and refinement. See, when some data doesn't fit, it forces scientists to ask some really tough questions. Is my measurement wrong? Is there something I'm not accounting for? Or is my model incomplete? And that's what drives science forward, that constant process of questioning, adjusting, and refining the model to get a better and better fit over time.
So why? Why do we have to do all of this? Why is this whole fitting business so absolutely essential to science? Well, the reason goes way deeper than just methodology. It's about the fundamental nature of reality versus the fundamental nature of our minds. Think about your own experience of the world. It's just a continuous flow, isn't it? Time doesn't tick by in little boxes. Motion is smooth. Everything is connected. Reality is this seamless, fluid stream. But then look at our scientific theories. They're the complete opposite. They're built on discrete, separate, formal concepts. They use numbers, categories, equations, all tools that are designed to chop that seamless reality up into neat, manageable little pieces. And that right there is the fundamental gap. The famous mathematician Henri Poincaré actually gave it a name. He called it the discontinuity jump. It's that massive cognitive leap you have to make to get from the fluid world of experience to the formal, boxed-in world of ideas. And scientific fitting? Well, that's the bridge. That's the practical, step-by-step method that science invented to get us across that huge chasm. So when you understand this, it really changes how you think about science, doesn't it? It's not just a perfect mirror held up to reality. It's something much more active, much more dynamic, something that is constructed. So let's wrap this up and look at the big takeaways here. Okay, so what have we learned? First off, science isn't just passive discovery. It's an active process of construction. Second, those amazing theories we have, they're powerful idealizations, and they always need to be carefully fitted back to reality. Third, that gap between our experience and our theories is real, and it's a fundamental challenge science is always working to overcome. And maybe most importantly, objectivity isn't just something you find lying around. It's something that is achieved through that tough, endless cycle of fitting, testing, and refining. And this leaves us with one last big question to chew on. If science really works by actively fitting messy reality into our clean, human-made theories, what does that actually mean for the whole idea of objective truth? It kind of suggests that truth isn't something we just find, like a rock on the ground. Maybe it's something we build, piece by careful piece. Something to think about. Thanks for joining me.